All right, we are broadcasting. Hello, today I'm going to talk about XLNet, Generalized Autoregressive Pretraining for Language Understanding. This is a paper built with Carnegie Mellon and Google Brain. I am Leonardo Apolonio, and I'm going to be giving a high-level overview of the paper. So the outline is motivate why did they write this paper, a high level intuition about how the network architecture actually works, some implementation details about how they got their unique approach to actually, converge and actually solve the problems that they were intending to solve, and then some, pointing you to some resources that I use in order to put together this presentation. So the motivation. Uh, Language, the current approaches to language modeling have strengths and weaknesses. There are currently two approaches, uh, autoaggressive and autoencoding language models. An example of autoaggressive is the LSTM. So how that works is given a sequence of tokens like, current language modeling, you want to predict the next word approaches. And you can build language models uh, autoaggressive language models using one direction, either sent words from left to right or right to left. So weaknesses and strengths will predict have. Uh, these language models are not effective at modeling deep bidirectional contexts. So if you think about intuitively in a sentence, there are words that will either, reference words before or other words that reference after that word, and a autoregressive approach will not be able to capture those relationships and contexts. Uh, that weakness results in a gap between the autoregressive language models and the pre-training required to solve downstream tasks. The other approach is autoencoding language models. For example, BERT. So the idea is that you try to reconstruct an original sentence from corrupted output. So BERT would actually use a mask token. So uh, instead of uh, predicting approaches, you would input a mask, literally the word mask, and given all the words in the sentence around approaches, you would try to predict approaches. Uh, the implementation of actually adding that mask token is absent from fine-tuning your task for your downstream tasks. So that creates a discrepancy between how you built your language model versus the actual um, downstream task that you're trying to solve. So let's go into a high-level intuition about how XLNet actually works. First, let's start with BERT. So given the sentence, I like cats more than dogs, you will try to predict the word cats and then, and that will be done by actually masking or replacing those target words with actually a mask token. So BERT will actually use all of the non-mask tokens to predict the masked tokens. And that's how BERT works. So XLNet actually does not use the mask token and actually creates a random permutation of the sentence. So given there are lots of different permutations of I like cats more than dogs. However, let's just take one example. Cats than I, more dogs like. And what happens is each word will be predicted using the words before that random permutation. So for instance, uh, you'll try to predict more given the words cat than I, given the context cat than I. And you'll try to predict the word cats using no words, and you'll try to predict the word like using all words in the sentence. So the permutation order only dictates the context of the words used to predict your target word. It does not actually permute the actual original sentence words. So you can think of your XLNet architecture, and the last example that you're trying to predict is like, and you're actually using all the words previous to like in the permutation order. So for another example is you're predicting then, the word then, using the words previous to that word in the permutation order. Credit to ML Explained, the XLNet blog post in order to create this actual graphic. What isn't shown is that there's actually also a hidden state memory hidden memory state in order that's also as input that will actually help you also predict the target word. So there are now onto implementation details where you actually have the problem where the example when you predict the word then and given that same sentence the when you try to predict like, when you use this sentence to predict like, it actually contains the answer to when you tried to predict then. So the implementation details actually go over how do you actually prevent separate examples from the same sentence to actually stop each other from giving the answer. So again, when you try to predict the word like, that actually this target like, predicting the word like, actually contains the answer to another example when you tried to predict the word then. A naive implementation will actually expose the word or the answer when you try to predict that. So the XLNet actually introduces the content stream and a query stream. And so the content stream works very similar to BERT. However, they mask the order that is used in order to predict that word. So here we have another example permutation order, 3, 2, 4, 1. And so the first word in this that's being predicted from this sentence is at position 3. The second word being predicted is at position 2. The fourth word being predicted is at position 4. And position 4 actually uses the context of 3 and 2. And we can see that over here. So we're the original order of the sentence, 1, 2, 3, 4. And we're trying to create a hidden stat based on the word at position 4. And this word at position 4 actually has access to the word at 2, the word at 3, and I'll show this memory state. And then another example, the word 3 only has, since this is the first word in the permutation order, it only has access to the hidden memory state. So this hidden memory state is using the hidden memory and the context based on the permutation order in order to create a hidden context for that word. So what's happening is you're using random orders in the sentence in order to predict or create an understanding of that word at that location. So in order to prevent a sort of peaking into the future across examples for the same sentence, they also create what's called a query stream that's actually being built in parallel to the content stream. And so now we're going to talk about the query stream, where we have the same factorization order. However, in order to overcome that peaking, they actually use what's a positional encoding, which is represented at W. And so if we look, the word for or the word at 4, the position 4 view, which has access to 3 and 2, we actually use the words or the words at 3 and 2. However, at position 4, instead of the content or the word for, we're actually going to use a positional encoding that's being built that is at word for. So the idea here is that you want to use the location of the word in order to predict the word, in order to build your language model. So you think about the distribution of words at the beginning of your sentence is different than the distribution of words inherently different than the words at the end of the sentence. Whereas in your content stream, you're using the actual words, a random selection of words around the target word in order to understand that word. So we have what words are around you, how do those words around you affect, how do the words around you create a context and affect your understanding of the word you care about, versus how does the position of the word, of where the word you're trying to predict and that context play together in order to create a representation. So, and so that's the main implementation detail that differentiates the XLNet architecture. Here I thought it would be important to actually go over the ablation study. An ablation study is a way for the authors to sort of help the readers understand the architecture decisions so that we can understand how exactly those design decisions affect performance. So all models are 12-layer architecture, and they were built using Wikipedia and the book corpus. And they're actually reported the median of 5 runs, which is pretty intense. That means they ran each of these models 5 times, and they returned the median of those 5. So we have here the first model is BERT-based, which uses positional encodings, next sentence prediction, the denoising autoencoder, that mask token. Those are the main BERT architecture decisions. And so that's our sort of like our baseline. And we see that using Transformer XL, which is pretty much transformers, but with in comparison to BERT, this does not have the next sentence prediction. And in addition, it also has this memory state. So you take Transformer XL, the memory state in Transformers, you add on the mask token, and we see that increases performance across the board. Race is a reading comprehension. Squad is a question answering task. MNLI is a inference test or natural language inference task, where you try to predict if these two sentences are related to each other or not related to each other, or if you can infer one sentence based on another sentence. And then SS2 is a Stanford sentiment tree bank task. So they see here, so back to our ablation study, or their ablation study, they took Transformer XL, added the mask design architecture choice, and we see consistent improvement over BERT-based, except for the sentiment task. Then the next model they compared is the XLNet base. The K actually represents the number of words that were used as a context, and we see that you get performance boost over BERT base and the transformer XL, and that's fairly consistent boost except for the standard sentiment tree bank task. And so the next example is k equals 6, which is a smaller context, and this is what's used in order to compare the actual design decisions of XLNet. So they removed the memory component, and we see consistent degradation across the board. So that's an important design decision. Span-based prediction is when you actually try to predict, instead of single words, you actually predict sequences of words. So like 2, 3, 4 words in a row, and try to predict those words all at the same time. And we see that in comparison to base, when you remove the span-based prediction, you see a consistent degradation in model performance. You see that memory is one of the even more important, because memory has an even bigger job than the span-based prediction. This, training decision. Bidirectional data. So that's when you actually are preventing the model from using the context in both directions. You actually have to use one direction, either right to left or left to right. And in comparison to XLNet, this is an even less important design decision than memory and span-based prediction, because the difference between the base and the bidirectional is even less than span-based and memory. And one interesting note about XLNet is that they did not use the next sentence prediction because they weren't able to get consistent task performance or downstream task performance improvement. So when they add that, they only get state-of-the-art for the reading comprehension. But if you look at the rest, you actually get degradation when you take XLNet base and you add next sentence prediction. You actually get degradations in a number of the other tasks. So to create this presentation, I referenced, of course, the original paper. I used and read the ML Explained blog post. I also used the graphic from this page. There are a number of other people who are giving presentations and explanations. One is the Feedly group, the NLP Breakfast Series, where they actually went over XLNet. And currently, the Kaggle Reading Group is going over the XLNet paper. If you have any questions or comments, you can reach out to me here on this video or on Twitter. Thank you for watching.